All right, good morning, everyone. This is Kyle Welch with RCR Wireless News. I want to thank everyone for attending Redefining the Signaling Landscape for Service Agility, presented by NetNumber. Our presenters today are Sue Rudd, Service Provider and Analysis at Strategy Analytics, Doug Rinaldi, Founder and Chief Strategy Officer at NetNumber, and Brad Boston, President and CEO at NetNumber. At this time, I'd like to pass the presentation over to Sue.
Thank you very much. I'd like to set the stage for this discussion and talk about why signaling, which has traditionally been the stepchild, perhaps, of some of the recent network architecture discussions, really needs to become center stage. And we really need to look at how the new signaling architecture needs to work with the next generation network architecture. And this is because a lot of trends are driving some really complicated issues. Let's start with the first one, which is the diversity of applications. What we're looking at here is the whole range of voice, fixed voice, interworking with mobile voice, 2G, 3G, and now VoLTE, working with IMS and VoIP, doing SIP interoperability with VoLTE, and CS fallback for VoLTE calls that can't complete on another VoLTE network, as well as the evolution of messaging, which has got the legacy apps, the walled garden apps, and then in many cases the over-the-top apps that in fact trigger quite a lot of policy issues in signaling themselves, as well as the wide variety of data access protocols that are all now requesting bandwidth and requiring end-to-end validation, so that we have as a result a whole range of protocols that the signaling community has essentially evolved over the years, but now they all need to interoperate. And we've got a very complex world, all the way from TCAP and the legacy ISDN protocols and ISUP, as well as MAP, the mobile protocols, SIP, the over-the-top apps guys, ENUM, which is the mapping of mobile numbers or telephone numbers in general to IP addresses, Radius, which is your AAA authentication for Wi-Fi, and Diameter. So let's look at the next step, which is required on the next slide. We have some real issues in how to handle the signaling storms that may be created by not only the diversity of protocols, by the continuous queries and pings that may occur to the network from applications like over-the-top, but as well as from IoT, Internet of Things, and M2M requirements. We may end up with a massive number of applications that require synchronization or some level of alert and update. There's a great concern by many of the mobile operators that in fact we're going to have to optimize our signaling network without necessarily having associated revenue. And so one of the real keys to this whole world is to manage that signaling storm or potential storm without upsetting the amount of traffic and network provisioning we have to do. The example shown here is just a simple example of how a single subscriber transaction request can trigger up to 16 additional signaling messages on the network. And although these are triggered at the edge, they may have to go across to the core, back again, and iterate a number of transactions. So what does this mean in terms of expected signaling traffic? Let's look on the next slide. We're seeing some forecasts. These are some that Oracle kindly published back in 2013 of just how fast network signaling traffic could grow. And this is based on a sort of base level view if we don't optimize some of the applications, and especially policy applications, which as we get into all the real-time management of the interworking of systems with rules for network traffic management, but also user interactions with the system to place policy requests or changes in billing, changes for priority of traffic and willingness to delay traffic, all of which can end up with a policy request going across the network and impacting the signaling network. OCS, which is your real-time billing system, is also going to be one of the major areas where we see enormous traffic growth. And in fact, the growth that we're projecting to see could be greater than the actual data user traffic itself. This could cause some significant financial burdens on the operators unless we really optimize that. And although it's important to deal with the traffic growth, perhaps we can look at ways that we don't have to send quite as many transactions all the way across the network. But we have to do whatever the traffic requires within milliseconds, seconds, and seconds. And we'd have to do it across an amazing number of the applications, as I mentioned, all the way from voice and VoLTE to IMS and SIP, and the whole new version of VNF, and virtual network functionality being put together in a virtualized world, perhaps on the fly, so that if we don't abstract the VNFs correctly, the virtual network functional elements, we may have a huge burden just reassembling our virtual network functionality. So let's look at some of the solutions that have been proposed on the next slide. We're going to talk about why we have to think about this in terms of the architecture that we really need to move to. At the top here, I've shown how the network functionality is evolving. And at the bottom, some suggestions or some thoughts about how the signaling functionality has to go with it. As we've seen in the last couple of years, going even faster than I originally put together on this roadmap about a year ago, the signaling capabilities for call management, session management, now flow management, all becoming very much more important in the network operations. Enabling the network function virtualization, simplifying addressing and traffic management, much more traffic steering in real time, and then as we go forward into the true NFV SDN world, enabling service orchestration and optimizing the profiles of users, their applications, their flows, and all the devices they have in real time to optimize the end-to-end delivery of good quality service. So that's what the network has to do, but what are the associated things the signaling network has to do? As I mentioned, NFV itself can generate a lot of signaling traffic, assembling the newly abstracted layers of network elements to reconfigure resources on the fly, as well as the virtual network functions on the fly. But we also have to manage end-to-end service assurance and make sure that the policy enforcement rules are set at the edge as well as across the network. I put user-defined networks here. AT&T is now talking about network on demand, by which they mean an Ethernet access on demand, but even users defining their own VPNs on demand. And we're actually seeing this start to roll out right here at the end of 2014 with a committed rollout in 2015, although many of the operators will not really move to that kind of architecture for true SDN until 2016. But we do expect to see an increasing demand for the signaling and control plane capabilities come with SDN. And this all has to be in real time, network-wide, under some kind of stateful management control with open service APIs. A wonderful dynamic world, but a tremendous burden on the signaling network that has to be optimized. So let's look at some of the ways that people have discussed doing that on the next slide. One of the service optimization approaches comes out of what is probably I would say, the killer app for SDN, which is the definition of VPNs on the fly. This is an Ericsson example, but it is one that is used by many of the vendors. And as I mentioned, AT&T's earliest service is a precursor to a user-defined network-on-demand VPN. And one of the keys to doing this efficiently without overburdening the signaling network is only to provision and involve the network elements that are required. Traditionally, all network elements were enabled for a service, even if much of the element processing did not actually need to go through that. And so what you see in service chaining is an ability to optimize only the network elements that need to be activated for a service. And in this case, you see the red line allows you to identify which are the ones that have to be were originally involved in the path, and now we have the blue line with the optimized logic path, taking a much faster, simpler route that directly assigns bandwidth for the on-demand VPN. So we can, in fact, simplify the service logic flow and, as a result, simplify the signaling to go with it. But what else do we have to do? Let's look on the next slide. One of the things we have to deal with is the domains of performance that this requires, and this is not often discussed enough. On the left, we show things that happen in seconds, which are the policy requests and the user requests for new OSS capabilities. And the control and forwarding plane needs to happen in milliseconds. It probably is something that can be achieved on bare metal hardware, although with difficulty. In the middle there, we're showing some of the really high performance things that have to be done with the SDN controller. And many of the vendors are still wrestling with how to deal with what I will call the nanosecond, sub-millisecond requirements. We really have to have very high performance real time, sometimes even nanosecond. Some of the platform vendors like HP are actually dealing with classes of performance that are required in different network function virtualization platforms. But the signaling platform itself has to be able to deal with this very high performance domain for activating elements and sending the forwarding information to all the different elements in the network. And then finally, we have the less demanding domain where we see a tremendous focus and a tremendous opportunity for automating the BSS OSS domain and orchestrating a lot of cloud administrative functions, things that happen in human time with the service catalog and the actual order placement. But as we optimize the signaling elements, we also need to optimize which performance domain they require. And so this is, again, a really critical element of looking at how do we ensure we have the TDM performance in our new IP and next generation signaling networks. Next slide, please. I don't want to go through this slide, but I wanted to show you that even way back in 2010, AT&T was talking about how to optimize the low-performance OSS domain separately from the runtime execution environment. And I think we need to go back and revisit the performance of the signaling required to really make that happen. As you see at the bottom of the slide, all the elements of service control, SIP call control, customer service interoperability, as well as all the traffic routing and the interaction with the IP MPLS core network. And this architecture, although it looks very complicated, is in fact the beginnings of what we see today with the next generation architecture. But we now need a signaling architecture to go along with this. So let's look at that on the next slide. What we need to do is to be able to centralize and control the entire environment on a logical basis. But there are dangers if we try to do that also on a physical basis. And this shows an example of a typical combination of CSCF functions being combined with automated signaling between application platforms and all the mobile elements to see if we can bring together an optimized end-to-end control plane and do all the signaling functions required to support that. But to do that, we have to be careful not to develop a centralized bottleneck as a result of our need to logically, but not necessarily physically, centralize the signaling elements. And if we're not careful, what has traditionally been our convenient way to do architecture for signaling with a centralized diameter signaling controller may in fact become a real problem unless we can architect the signaling network as a network in its own right, with some functions centralized and tightly coupled, and those functions that need to be localized distributed closer to the edge to avoid the signaling bottleneck and excessive backhaul traffic. So what are the kinds of solutions? So let me start to hand it over to Doug, and he can talk about some of the signaling complexity that we have to handle and maybe some approaches on how to do that. Doug.
Sue, thank you very much. Good morning, everyone. This is Doug Rinaldi, founder and Chief Strategy Officer here at NetNumber. I want to start with the background Sue's provided that describes an industry problem of growing signaling complexity that we all need to deal with at some level. Let's take a look at that from an architectural perspective, and then we'll try and break the problem apart and see if we can see a path forward to resolution. So on the screen in front of you, what you've got is high-level network architecture diagram. I'm sure most of the people on this call have seen variations of this slide before. It shows a converged network. On the left, you've got diameter, LTE, services and functions. Over on the far right, you've got the legacy SS7, C7 TDM network, its functions and services. In the middle, we've got the IMS core, all of its functions, and then gluing all of this together, ENUM and DNS. So we learned a couple of things from this slide. First, A converged network architecture is complicated. It's complicated because as an industry, we wanted the flexibility of breaking out all of the logical functions into well-defined components that have standardized interfaces between them. We did this to enable vendor interoperability and to enable service providers to have vendor independence. You can buy one function from one vendor, buy another function from another vendor, and get them to interoperate. So at NetNumber, we're a big advocate of standardized interfaces. But with any strategic objective, sometimes you have a risk of going too far. This picture shows us an enormous number of functional elements. If we go about deploying the network where each of these functions is implemented as a standalone silo platform that has to be licensed, integrated into network management, deployed in the network, operated by the support staff in the network, upgraded in its life cycle, monitored, managed, what you end up with is a very complicated network and an expensive network to operate. You also end up with the problem of service agility. What happens when the marketing team comes up with a good idea and they need to create a new end user experience? Might sound like a simple idea, but if it touches 7 or 8 devices in this network, how do you actually achieve that? How do you cause the different vendors to align their release roadmaps to enable the change that you're looking for to fulfill your goal in the market? The fact that we've separated all these functions out actually creates a service agility problem. So now NetNumber, we look at just the signaling control aspect of this. So on the next slide, what we've done is we've highlighted what are the functions in this architecture that are actually purely signaling control or network database services. So these are functions that allow switching elements or policy elements to access data or talk to each other. That's the realm of signaling control. And we've already discussed that functionality cuts across many protocols, as Sue pointed out. SS7C7, SIGTRAN, Diameter, ENUM, DNS, and SIP. We've got that legacy, and we're going to live with that legacy of many protocols for a long time. Now, from our perspective, if we implement all of those signaling control functions as separate elements, we end up with a network that's too expensive to operate, and we end up with a network that simply lacks service agility. You just can't make changes fast enough. So what we've navigated to as a company is designed a signaling control platform. That platform we call today a CSRC, a centralized signaling routing control platform. Now, our particular product that implements that CSRC function is called Titan. That's NetNumber's core signaling and routing control platform. But the function of centralized signaling control, we believe, is a key leap forward in the thinking of how you manage signaling complexity. Here on the slide in front of you now, you see how simple the network looks if you take all of those signaling control functions and think of them as simply applications. Our salespeople love to tell the story of, imagine you've got an iPhone and you want a new application. Today, life's quite easy. You just download the new application. But imagine a world where that wasn't possible. Imagine a world where every application required its own physical infrastructure. So if you had 17 applications, you had 17 iPhones. It's a great visualization of how complicated the world is if you try to run every application as a standalone physical infrastructure. Just visualize carrying around 17 iPhones. Alternatively, one iPhone, or in this case, a CSRC, that runs many logical functions. Now, if you want to make changes to that functionality, you deal with one spot to make the changes. You can make changes quickly, and it's easy to maintain that relationship. Now, centralizing that functionality introduces its own challenges. So I'm going to jump for a second and now talk about how did NetNumber go about implementing this CSRC platform. So first we get the marketing picture. Titan is the core platform. You load onto Titan many applications. We've color-coded them by protocol. So you've got ENUM DNS applications, SIP applications in yellow, diameter applications in purple, SS7C7 SIGTRAN applications in green. One of the features this points out is interworking is actually a requirement in our networks today. You're constantly going to encounter situations where a signaling message comes in one protocol, say SIP, and you need access to data over a different protocol, SS7. So interworking between protocols is a practical requirement. By implementing a CSRC, that actually becomes quite simple. One platform supports many protocols. Interworking becomes easy. Let's jump now into the details of that CSRC implementation in Titan. Next slide, please. So inside our Titan platform architecture, there's really three areas of activity that we're involved in. At the top layer, you see the database. The core of Titan is a scalable distributed database. It's single point of provisioning with the OSS BSS layer. So you put the data in one spot. You'll see in a subsequent slide, we take that data and we distribute it to multiple protocol edge servers so that it can be widely distributed in the network. Because although we say centralized, that doesn't mean one instance or one box. That's not possible. The system has to scale, and the system has to be resilient. So you need to put data in one spot, but you don't want to leave the data in one spot. You want to be able to distribute it out for both resilience and speed of access. On the other side of the platform, we have the network access. So the signaling interfaces. You see in this picture, one platform that supports all the signaling protocols. We're not the only vendor in the world that sees it this way, but it's instructive to stare at all those protocols because we're stuck with them for decades. It's just the way we've evolved our networks. In between the data and the signaling interfaces becomes a requirement for application logic. STP application logic, HSS application logic, ICSCF application logic, ENUM application logic, DNS application logic. In truth, all of these functions that I just mentioned, they're all signaling control. They're all well-defined logical functions in the network that communicate over some standardized interface, and they need access to data in order to complete their job. But other than that, it's just some logic. So yes, we could separate them all as separate physical functions, like you'd have 17 iPhones, or you can view them as simply applications you download to the CSRC. We think it's a dramatic improvement in both operating costs and service agility. Now, before I turn it back over to Sue or Brad, let me talk for a moment about the idea of distributing this CSRC across the network. So we'd switch to the next slide for me. This is kind of a stylized description of what Titan looks like in its master edge architecture. You see over on the right-hand side a bunch of OSS, BSS systems that interact with signaling control, meaning they put data in or they get CDRs or network events back. So the CSRC provides a single interface to OSS, BSS. That in itself simplifies your life. But once the data is in that master application, we believe it needs to be distributed in real time out to a widely distributed constellation of edge servers. Those could be physical or virtual, but it needs to be widely distributed for both resilience and for reducing the latency of signaling control response time. We operate in a world where networks span very large geographies. So backhauling everything to one spot creates its own bottleneck in the network and its own risk. To fix that, we believe you need to distribute the data out to that constellation of edge servers. So with that background, I'm going to stop for a moment, switch this over to Brad Boston, give you a little background on NetNumber, and then I'll come back and talk about some use cases.
Thank you, Doug. So NetNumber, we've been around for about 15 years. I just celebrated our 15th anniversary. As you heard, we have Titan as our flagship centralized signaling and routing control platform. We also provide global data services for number portability and global block data. And in North America, we own all of the MVNO override data for the industry and distribute that out to other players. We have a large suite of applications, as Doug discussed, and we've been profitable since 2007. We have no debt, and we're still privately held. Next slide. We have a tremendous customer and partner base. We have over 150 customers worldwide that either use Titan deployed in their networks or use a cloud-based service that we provide for number portability access. So we have top-tier carriers throughout the world in the fixed line business, the mobile business, and the cable industry. And we also have some great users of some of the over-the-top services such as Google Voice and others. And then a year ago, we started a very formal partner program and have established some very strong partnerships with other players in the industry, such as Genband, Alcatel-Lucent, Nokia Networks, and Metaswitch, and Dimension Data. So we've got a number of good partners that we are working with to bring total solutions to our customers and also to expand our ability to reach and distribute our solution to a broader set of prospects worldwide. Next slide. I want to talk for a minute about some deployment considerations that we think are pretty unique. So we can deploy Titan on traditional hardware. So we bundle it up on off-the-shelf commercial servers and deliver that to the operator's own operating environment. And we support all the technologies that we need to interface with in order to do that. We have a good high availability platform. The edges work extremely well, and we recently introduced some additional enhancements at the master to allow an N-way master configuration to be deployed. We currently run in production in virtualized environments today. Today we are deployed with a VMware hypervisor, and we're in the process of deploying with KVM as well. We recently also deployed on a Linux operating system. Interesting history, back in the early 2000s, we first delivered our product on Linux. None of our customers wanted to see Linux anywhere near their operations, so we had to switch to Sun Solaris. And so we've been deploying on Solaris ever since then, and now the movement back to Linux has brought us a complete circle, and we now are deploying on Linux and have our first production environment in Linux deployed last quarter. And then we run a cloud service that supports probably 75, 80 different customers to do provide numbering data services, number portability in particular, to people like Google Voice, and even to large carriers such as AT&T uses it for their MMS business. And that's been a nice, profitable business for us and has been growing very nicely. Next slide. One of the things that we think is unique about the Titan platform, in particular as you think about what's going on with network function virtualization, is that we see all of the players that deliver those standard appliances that make up all those different components on the architecture chart that Doug showed. They're all virtualizing those appliances. But that's a very complicated, complex environment with very complicated and complex interworking between the different components in that architecture. So scaling that fairly chaotic environment automatically with the NFV infrastructures that the carriers are looking at is a very, very complex task and very difficult. We've talked to one carrier that's tried to do that in the lab and found that it just didn't work for them. So we have this line that virtualizing chaos is still chaos. And so if you want to go and bring those functions into a virtualized and an NFV environment, it's much easier to create an environment that you can scale up and scale down when you go and consolidate as many of those different appliances onto one platform as you can. Now, no carrier today consolidates all of those appliances, but we have several carriers today that have 5 or 6 of those applications all running on one footprint. And to scale that up is much easier than having to scale up 6 different appliances and reconstruct all of the different interactions that they have to do with the other components in the network. So we think we have a very, very powerful story and solution for those carriers that are looking to evolve to NFV infrastructure, and that we have a much more dramatic way of simplifying the environment that allows them to scale up and scale down much more easily. So with that, I'll turn it back over to Doug to talk about some specific use cases.
Great, thanks, Brad. I got 3 use cases to walk through. Just give you a perspective of interesting ways that we've seen customers utilize the CSRC concept to solve practical problems. So first is an interworking example. I discussed that in my earlier notes of this is going to be a constant problem for us because we have so many protocols. Interworking is just part of life. So here we have a case of a mobile operator migrating subscribers from their existing 3G network over to voice over LTE. At the same time, this operator decided to switch their interconnect model over to SIP. So they wanted to receive inbound traffic via SIP. They immediately ran into a problem. SIP invite comes into the network and it hits an SBC at the edge of the network. Right at that point, the SBC has absolutely no idea, is this subscriber served in the 3G network or in the IMS network? And so, absent a way to answer that question, the operator was routing every call to a gateway MSC, which had the ability to do map and camel signaling to see if they're in the 3G network. If they weren't in the 3G network, it would default route, it would proxy the call to an ICSCF at the edge of the IMS network, where the ICSCF could interrogate the HSS to see if the user is in the IMS network. Ultimately, the goal being get to the serving call state control function. The problem here was that discovering the subscriber is split across several different protocols, and the SBC didn't have that skill. So what the customer did, they implemented the Titan CSRC. The SBC sends an invite to Titan. Titan queries the HLR, queries the INSCP. If it's not in the 3G network, queries the HSS, discovers the currently assigned SCSCF, and proxies the call or redirects to the SCSCF. What we achieved with this is faster call setup and significant reduction in the average number of assets involved in every call. In the previous scenario, Gateway MSC, ICSCF was involved in every single call to IMS. So the network was wasting assets because it couldn't find the subscriber because of this protocol interworking problem. The CSRC provided a creative solution. Next slide. This next case is a case of a centralized routing use case. Here we're talking about a next generation interconnect provider or IPX provider. We know from history that interconnect providers operate on very thin margins, right? In order to succeed in that business, you've got to figure out how to squeeze every bit of complexity out of the network and every bit of cost, because pumping a huge amount of traffic through at very low margin is the only way to win in that business. So this particular customer wanted to interconnect traffic either via TDM or via SIP. So they were deploying media gateway controllers at the edge of their network for TDM and SBCs at the edge of their network for SIP. What was needed was, how do you interconnect that? How do you route between those services? If we look at the legacy of our industry, the way we would do that is with a class 4 interconnect switch. So at the edge, you'd pass the call to some interconnect switch in the core of the network, and it would make a routing decision. This IPX provider didn't want that cost. What they wanted was simply the signaling control. They just wanted to know, how do I route this call? They didn't want a centralized class 4 infrastructure to be involved in every call. They just wanted the information, the signaling knowledge. So they deployed the Titan CSRC. What we achieved was reduced network complexity, centralized routing updates that happen in real time, faster deployment of new services, and reduced operating costs. Got one more use case. It's an interesting one we never anticipated. End-of-life STPs. So when we started down this path of the CSRC, in truth, we thought the SS7 network would be shut down quite some time ago. You know, Brad mentioned we've been at this 15 years. I think everybody, if you look at the industry 15 years ago, thought we would have moved beyond TDM by this time. Turns out that's not the case. We're going to be living with the TDM network for another 15 or 20 years. But in the intervening period, vendors in this space have declared the vast majority of STPs in the world end of life. So we've got thousands of networks with STPs that are end of life, and there's no more development on them. So when you encounter a new service requirement, someone comes up with a good idea to add value to the network, you can't do it because the STP doesn't support any changes anymore. So surprisingly, the STP becomes one of the great applications for a CSRC. You could turn down that silo infrastructure, move the logic to the CSRC, and at this point, you've got a platform that you can build on to support all of your future signaling control. You've reduced one silo, and you have a path forward for making service changes. So we see huge growth in STP replacement in this CSRC market over the next 10 years. With that, I'd like to turn it back to Sue Rudd.
Thank you very much indeed, Doug. So let's translate all of this into the business benefits for service providers. And this is probably, they're under tremendous pressure on their investment side. They're under pressure on the margins with dramatically growth in traffic, but not the comparable growth in revenue. And what they really need is to optimize the performance of the signaling network as well as the network in general. So we've put together a summary of the benefits here. And let's look at the configurable platforms, the need for a flexible development environment, need for virtualization that's coming, scalability, and support for legacy as well as new protocols. Next slide, please. This is a chart that we have in the white paper that when you when you end the webinar, you can submit a request and get a copy of the white paper from the NetNumber site. But just to go down the left-hand side, the features that were just listed, the need to get a configurable platform, as you heard Doug describe, the iPhone model where you can have one application layered on another. Once you have the anchor platform, you can layer on the incremental value-added applications and have guaranteed interworking. And again, they could be interworking with other vendors as well, but once you've established it and defined all the interfaces, then you don't have to do it again to replicate instances of that platform at the edge or in the core. The scalability of databases, and we don't have time to go into that a lot today, but really critical in the long term for mapping all these new network elements, whether it's Internet of Things, whether it's all of the VNFs, the virtualized network function, need to have a router element as well as an actual access and properties associated with them. We're going to be needing this in order to manage our new HSS capability and all of the service profile repository capabilities as we personalize services. So dramatic expansion in the need to identify more things, more locations, and route traffic between them. The performance in virtualization, I think, is something that every operator is demanding in their RFPs based on some of the surveys we've done lately. And to do that, you can virtualize your legacy equipment as a start and gain a lot of the network operations value. But to gain the service agility value, which is what a lot of operators are after, is really essential to be able to take the service elements, and Doug described some very nice examples of how you can actually mix and match some of these elements and add a new set of service functionality out of existing components, and then be able to trigger a new service and deploy it and activate the service elements, something that's not often talked about when we talk about creating new services. And this is really important part of how the signaling environment operates with the service logic environment. And then we have, of course, the legacy protocols that we've spent a lot of time discussing today, but being able to interoperate seamlessly, as Doug showed in some of a couple of the use cases, really makes a difference on the bottom line. Not putting and having to maintain a lot of legacy class 4s or a lot of interworking equipment with separate gateways to get between all these networks that are going to live with us for at least 15 or 20 years. And the CapEx and the network costs of operating these environments are dramatically impacted if we can come up with a simpler way to do that. And then finally, and not least in importance, is to think of this as a real-time stateful network in an IP world. And although we're going to an all-IP world where everything is packet-based, we need to have the performance of our environment be that of an event-based transaction processing world, and to be able to do that efficiently and to get the service agility that we need. So with that, let me hand it back and see if there is any questions. Kyle, do you want to see if we've got any questions? Or
Yeah, thanks, Sue. Yeah, we've had a couple questions come in. The first one is for you, Sue. So how does the new architecture save money for service providers?
Well, we've mentioned a couple of them, but let me just summarize it. There are really several ways that they saves money. Probably the most important one is that you actually reduce the signaling traffic volume. I showed the need to do that up front, and then Doug described some ways that, in fact, will dramatically impact the amount of signaling traffic that's actually transiting the network. And so we really need to think about not just optimizing a load of signaling that's done the same way we've always done it, but how to actually reduce the network load and associated processing costs. But importantly, it's the issue of how you distribute those database resources as we go forward to more personalized and unique individual services that AT&T is talking about, as well as many other operators. And we migrate to each service instance is almost mass customized around that particular user requirements, so that we can actually have the database resources with both centralized and localized access, so that we can instantly follow the kind of example that Doug showed for the HSS access anywhere from any network, whether it's the same protocol or not. And then third and most importantly, the real core platform. Once you have the right kind of core platform, then you can layer on these incremental functions, many of which we may not yet know what we need to do. But having an architecture that we can go to, that we can just layer on incremental functionality, as well as interface with multiple other vendors' functionality for very low cost. Doug, do you have any additional comments you would like to make?
I don't. I think you covered it beautifully. I'll just highlight that feature you just raised of managing for the unknown. We know that every 6 months, as we move forward with evolving these networks, we learn what we didn't know previously, and it requires you to make changes. It simply takes too long if you have to wait till you gather the knowledge, and then you have to negotiate with every vendor to get on everybody's roadmap to achieve an end result, and you're trying to coordinate across 17 different signaling control functions. You simply can't get it done. I think you highlighted a key point of you need to design the network to anticipate ongoing learning.
All right, great. Thank you, Doug and Sue, for that answer. Again, if anyone has any questions, please submit them to the questions tab in the control panel. So, Sue, another question we had come in that I thought would be best directed to start with you is, what impact do you think Internet of Things will have on signaling storms?
Well, many of the operators are very concerned. They see this great opportunity of handling a whole new network where devices talk to each other instead of people, and devices can be anywhere, very remote, very local, probably very low power and very low intelligence at one end, and then very smart and real-time high performance at the other end, so a tremendous diversity. But probably a huge percentage of those devices are going to be very low-end dumb devices, or relatively dumb, like remote sensors telling you when your golf course needs to be watered, or whether there's any alarms in your home. And a lot of those will be sending keep alive messages. If we don't design the network right, they'll constantly be bothering the network, just as we had problems in the early days of the smartphones when they constantly pinged the network, and each app on the phone was pinging the network to say, I'm here, I'm still here. And we really need to look at how we design the network, and in fact use some of the intelligence perhaps that we can implement with some of the signaling applications part to really manage the networks and only deal with those events that really need to be dealt with. Perhaps we can come up with some efficient ways to prevent that from creating a signaling storm. I don't know, Doug, have you got any thoughts on that?
Sure. I think it's all about scale and cost. As you point out, it's an explosion of endpoints, but very low value endpoints, meaning these don't generate much revenue per month per endpoint, but you got a huge number of them. And so suppressing traffic at the edge becomes critical, and designing an infrastructure that squeezes cost out is just necessary. Instead of an ARPU of $50 a month, you got an ARPU of 10 cents a month. It has to be you have to think differently. We built the network we're staring at today, anticipating a traditional ARPU of $50 a month. The Internet of Things changes that.
All right, great. Thanks for that response, Doug. Doug, we had a couple questions about Titan come in. So the first one is, how long does it take for NetNumber to add a new application to Titan? And is it a significant amount of work?
It's a great question. I'll take that. We have several of our large customers look at our story and they say, wow, that's so exciting, but how do I know I can count on NetNumber having the professional resources available to make incremental changes when I need them? At the high level, the answer is it's very quick to make changes. Service logic in Titan is programmed in Java. Very quick to make changes. We can often turn a change in a couple of hours for a customer. But that doesn't necessarily deal with the resource availability problem. So what we did is we've designed the platform with a application development framework where we can train our customers to build and modify their own applications. Right now, we only have one customer doing that. It's British Telecom, but it's been very successful for them. They add features, add applications, and only contact us if they choose to get input from us. Otherwise, they have total flexibility.
All right, thanks, Doug. Kind of as a follow-up to that, we had someone ask about the role of DRA, DEA in the Titan. Can you comment a little bit on that, if Titan actually replaces that or what role it does play?
Great. So right now, we are building out our diameter applications. In the circle of applications that I showed, we've got in production all the ENUM DNS, the SIP applications, the SS7 applications. But so far, on the diameter side, we just have applications on Titan where Titan is acting as a diameter endpoint, like an EIR or an HSS. We're not acting as a diameter signaling controller. We'll add that in 2015. When we look at it, that functionality, very, very similar to what we see out of an STP, different protocol, but you're talking about a router in the network. It routes signaling control messages. Sometimes it has to filter the messages. Sometimes it has to manipulate for network hiding. But in the end, it's just moving a message from point A to point B. What we actually see is going to occur in that market is we see the price is going to come down. Right now, the cost of diameter signaling controller solutions is relatively high because it's the newest thing in the network. I think you should anticipate those prices are going to come down.
I'd like to just add one component to that. One of the things we see or foresee our customers being able to do is by also provisioning into Titan some of the application data sources that the diameter router signaling controller or routing agent or whatever is trying to access. You can essentially eliminate some of the ongoing or forwarding diameter signal requests. So this is one of those examples of how you can change the volume of signaling going on in your network by combining a couple of the elements, the signaling controller and some of the data sources, into a single platform.
Thanks, Brad. Kind of on that, Brad, we had another question come in, which I think would be best for you to address. But anyways, sorry, Doug mentioned one of your customers using Titan. Do you have any use cases or examples of customers using Titan to solve M2M or IoT signaling challenges?
So we were talking to several customers about the M2M challenges that they're anticipating, and the whole issue of lots of signaling traffic for a lot of endpoints with very little data and very little revenue is a challenge that they can't economically solve in their current architecture today. So the idea of being able to provision the necessary data to a vast array of edges and put them out throughout the network and be able to intercept all of that signaling overhead as close as possible to the source of the M2M traffic is an attractive alternative to them, so that they're not having that onslaught of messages traverse their entire network to go back to a single location. So we're in early discussions with a couple of customers about how they can use Titan to solve that problem.
All right, thanks, Brad. So we have time for just a couple more questions here. So Doug, the next one, if STPs are going to be used for another dozen plus years or so, why have so many vendors ended their STPs at this point?
That's an excellent question. As I said, it caught us by surprise. I think it's just the reality we face as a business. We made a decision as an industry 20 years ago to move to IP, and that's a huge transition. Required development resources to be shifted, required new skills to be developed, and the result was resources simply got moved. Resources that were building and supporting and maintaining STP TDM technology, they transitioned because they needed to and they wanted to. And as a result, well, I think as an industry, we all envisioned a faster turn down of that TDM infrastructure than we actually achieved. So I think we just got caught by surprise.
Very interesting. Thank you. So it looks like we have time for just about one question. So Doug, I think this one would be best for you. What percentage of your customers do you estimate will do the SLEE customization themselves?
Excellent question. I think it's going to evolve over time. I think it starts with a small percentage, less than 10%, and then it evolves over time to more of a 50-50 model. And it just takes time for people to gain comfort. BT is a good example. For the first several years, they wanted NetNumber to make all the changes to their centralized routing solution. They just weren't quite ready for it, weren't confident enough. They gain experience, and then they test, make a small change, and it's like anything in life, you walk before you run. So this is something that starts small and grows. Eventually, could potentially grow to up to 50% of it could be built by our customers. No limitation on our part. I'm just speculating on what might happen in the market.
I'd just like to add that I think also the number of applications that a carrier deploys on Titan will have an influence on their decision to go and take on that support or not. If they're just deploying one simple application, such as an ENUM server, which a lot of customers do today, probably not enough there for them to go and have to develop and maintain that expertise. There's probably not enough changes going on for them to do it. But as they go and put more applications on, as BT did, I believe they run 4 different applications today and have several different data sources, and it becomes a bigger part of their signaling infrastructure, then it makes more sense for them to start taking on that challenge of doing the customization and their own company-specific service logic as a competitive advantage. It becomes more of an advantage for them to do that themselves. So I think it will happen, like Doug says, it will evolve, and part of the factors is how many different applications are they running on the platform.
All right, great. That's about all the time we have. I want to thank everyone for attending. Redefining the signaling landscape to deliver service agility, presented by NetNumber. Again, our presenters today were Sue Rudd, Service Provider Analysis at Strategy Analytics, Doug Rinaldi, Founder and Chief Strategy Officer at NetNumber, and Brad Boston, President and CEO at Number. Thank you for a great presentation, everyone.